going to have transform and conquer. Does anyone have any questions? Are you guys prepared for next week? So next week we have the quiz, sorry, the midterm. They should, perhaps have prepared for it. Okay, I'm just in the process of putting it up.
Can we talk about, there was something about one of the algorithms you showed us last week was it was n squared instead of n log n. Remember? I don't remember exactly which algorithm, but I think I figured it out.
Right. So if you tell me what's the question, you can post it in Slack, and if you know it now, you can ask it. But if you can,
let me look up which one. I think we were comparing something to merge sort in terms of time efficiency.
Okay. I don't recall, but if I know what I was talking about, I can have a discussion here. Okay, so if you guys go to content week 6, you should be able to pick up transform and conquer slides. So please go there, pick it up from D2O. I just put it there. I'm gonna share with you the slides. Okay. There we go. All right, so this is going to cover your chapter 6, and so basically, after chapter 6, we're going to look at space and time trade-offs, and then we're going to dive into the graph and treat, mostly graph theories, and that should conclude this class, because after the midterm, we only have 4 classes and the final, which the final is July 20th. You all know that. Okay, this is much better now. Okay, let's so Ray, did you answer your question?
Yeah, I found it. Okay, so on slide, it was definitely quicksort. So on slide 41 from last week.
41. Okay, so let me just go back to the slide 41 from last week. You're looking at the divide and conquer applications. Okay, yeah.
And
that question. Okay, go ahead.
So I think the reason that this is n squared instead of, like, the worst case running time is n squared is because I looked at the Masters theorem from the week before last, and like in case 2, it's like n log base b of a is greater than f of n, and f of n, I think, is it 0 because we're not merging? Like, there's no merges in quicksort. Like, I think it has to do with that.
So the question is why. So what the worst case is n squared, and why it is n squared, right? That's
yes.
what you're trying to answer. And then you have thought of a case that the array is already sorted. Right. So can you answer the question one more time?
Well, I mean, when I was looking at, I just went to the Masters theorem because I think in quicksort there's no merging, is there?
Exactly. Yeah. In quicksort, there's no merging there. Yeah.
F of n counts the merges, doesn't it?
Right. Yeah.
So I was just looking at the Masters theorem, and I thought n log base b of a is always going to be greater than f of n because f of n should be 0 for quicksort.
Right. Yeah. Yeah.
So I figured it would be n squared. I don't know if I did this right.
Okay. I see what you're saying. Okay. So you resorted to master theorem, all those three cases or three options that there was, and you compared the divide and conquer time with the Fn. And since that time is always greater than Fn, it's going to end up being n squared according to that formula.
Mm-hmm.
Oh, that's great. Okay, so this is one way to look at it because the formula has a proof. Obviously, we didn't cover the proof for it. The other way is to just heuristically find that it's n squared, and the way we find it is we look at the case where the array is sorted and see what's. It appears to be n squared because whenever the array is sorted, it's not n log. So if you want me, I can go back to my notes and basically bring you an example of n squared case for the quick sort. But your answer is correct.
Okay.
Yeah. That's great. That's a very excellent way of looking at it. I take a note in here. Did you also find an example for it?
No.
Okay.
No, I mean the way I answered the question was basically like the first step was like how do you evaluate running time, and that the answer is like use the Masters theorem. So I just tried to apply it, and I wondered if I did it correctly.
Yeah, that's a great way of looking at it. Yeah. Yeah, I also see if I can find an example for a case where it is n log n, whereas the worst case where it is n squared. Okay. So I have written a note here. I will update you on that this week. Any more questions? Are you guys all good? Okay. All right. So let's move on. One thing, I was marking the assignments, and I found that some of you are handwriting it. It's okay if you want to handwrite it, except that you would have to, how can I say, make it legible. Like I should be able to read it. So if you can turn it into a PDF and send it to me, or if you could possibly type it, that's even better. I sometimes find it hard or difficult to read your handwritten answers. So that's a problem on my side. Okay. Week 6. You guys see my slide shares? All right. So the two topics that we're going to cover today is basically has to do with we are transforming problems to make them look simpler and then solve it. And there are different ways that could be done. We are covering two of those cases, two of those techniques for transformation. The first one is called instance simplification, and the second one is called representation change. And so we're gonna spend the first hour for how we're gonna do instance simplification. We're gonna see some examples of how we're doing it, just to give you an idea, how things can happen to let it be in a simpler form to solve problems. And then for the second part of the lecture, we're gonna look into rep change. We can sometimes represent data or information in different format, and then that will solve many things in a better form. At the end of the class today, we have a couple of questions to solve, and that will be the last hour that we're going to spend for this class. So we have a problems instance, something that we have to solve. Either sorting, looking for something, or finding convex hull or closest pair. And the idea is to give it to some magic box that turns the problem into a simpler form, and then that gives you a solution that was the solution to your original problem. That's the main idea. So for instance simplification, it's also called pre-sorting. I tend to call it pre-processing. So here, sorting doesn't mean actual sorting; it means processing. So pre-sorting could also sometimes be called pre-processing. So we are looking at two examples. We're gonna check element uniqueness in an array. So I'm going to give you an array, and I'm going to tell you, okay, how can you find that all elements in an array are unique? And then we're going to look into a problem that is called mode problem. We're going to see what mode means in this context. For the second part, I'm going to introduce you heap. It's a new concept. And last but not least, we're going to add a new sorting algorithm, which is called heap sort, which is based on the heap structure, heap data structure. So these are the main topics of today's lecture. So the question is, what if you want to find an element or the property of uniqueness in an array? So let's say an array is given, array 1, 3, 5, 6, -1, 2, 10. So you have an array, and you want to make sure or find that all elements in this array are unique. In other words, there are no repeated digits in here. So let's say in the second array here, I call it L2. 1 is repeated 2 times. It's over here and here. Then 2 is repeated 3 times, right? 5 is repeated 2 times. So this array is not unique. So what's the basically bare approach to it? The bare approach is that we always try to solve problems with brute force. As I told you, when you are in an interview, that's the first approach you should take, and that gives you some time to think about, okay, if I want to go to divide and conquer, or I don't know, transform, conquer, and different types of algorithms for efficiency. So if I give you a problem like this, can someone tell me that how will you solve it? So the question is, write an algorithm that if all elements are unique in it, otherwise false. So can someone just describe to me a brute force algorithm for this? Someone other than Raid?
So you will have an outer for loop to control the first index, and then you have the inner out loop to go through the whole array to compare every element. So once that for loop is done, you go back to the outer for loop and then move on to the next number.
Exactly. So that's a correct answer. You're gonna have two for loops. You're gonna walk through. You're gonna keep your location, your first index at one element and compare it to others, obviously, and then you're gonna keep on doing that. So you would be having a one-on-one comparison as you walk through the array. So if I wanna write it down, quite a simple form, we're gonna end up with two for loops, and that two for loops would give us, time complexity of O squared. So let's do that. So I'm gonna have for I equal to 0 going to n minus 1, and then I'm gonna have for j equal to 0 going to, equal to 1. Or you could say I plus 1. That's even better, right? You could say I plus 1. Right? And then that's going to be, I think here you should put n minus 1 too. Okay. So in here you're going to compare, if let's say your array is called A, AI is equal to AJ, return false, right? And then at the end of the day, once you come out of this array, nothing has happened, so you're going to return true. Okay, so that's one case that you can write an algorithm as easy as that. And so as soon as we see two for loops there, as soon as we see two for loops, it's like sigma, I 0 n minus 1, j I plus 1 n minus 1 that gives you n squared. I mean 4n squared, right? So as soon as you see two for loops, that's quadratic right away. All right. So that's the brute force. So the brute force is n squared. And now the question is how we can improve this. Again, so this class is about finding your jobs, right? This class is about finding your jobs, and for that reason, you're looking at a strategy. So the first strategy is you provide this answer. You just basically provide this answer. You go to the whiteboard or whatever. If you're having a remote interview, whatever, you just say, okay, you just write this down, and then that gives you some time, and you have already brainstormed, right? Because I know the interviewer is going to ask, oh, okay, so what's the time efficiency of it, and then you can easily answer n squared and bring the same reasons I provided you with those sigmas. And once you do that, that just buys you time for improving it. And now the improvement is, in this class, is we're going to look at transform conquer with the first topic, which is 8-10 simplification. So the catch is sort by an efficient sorting algorithm. Let's just pick merge sort. The time efficiency of merge sort is n log n, right? And then we're gonna scan the array to check pairs of adjacent elements. That's all we have to do. So let's see how it goes. For the first part, since you have to sort it, you're gonna pick the most efficient sorting algorithm. The most efficient sorting algorithm to date we know has R of efficiency n log n. And then for the second part, it's just O(n) because you're comparing the adjacent all the way to the end. In the worst case, you are gonna go all the way to the end of the array. So that's for the stage 2, and that's for the stage 1. And you know that in combinatorials for big O notations, the bigger one will win, and then you're having a linear against a linear logarithmic. So the linear logarithm is going faster. So at the end of the day, you have used sorting as a pre-processing to simplify this question, to basically bring the efficiency from quadratic to linear logarithmic. So this is quadratic. Sorry, quadratic. When you use brute force, it's quadratic. And this is linear logarithmic, right? Okay. So that's just to give you an idea how we do things when we wanna look for something in an array, and then we're gonna decide. It's just one example that how sorting can come to our head. And so this is the algorithm for it, right? Pre-sort element uniqueness. You have the input is an array of orderable elements, right? That means that we assume that the elements can be ordered or are ordered, and then we're gonna return false if you find two adjacent values in an array are equal to each other. So this guy, in fact, should be something. This guy should be a comparatorial equivalence. So equal AI plus. Okay. So there's one equal missing here. So if that's the case, you return false. Otherwise, you return true. Okay. So once you sort, so let's say 1, 2, 5, 10, minus 1, 2, 3. Once you sort this array, it's going to be minus 1, 1, 2, 2, 3, 5, 10. Okay, and then you are going to end up to have a point that when you're comparing two adjacent elements, that's this guy, you're going to return false. Okay, so that means that you have found an element that is not unique in that array. Okay. Are there any questions so far? So basically, if you guys see, I'm starting to use the sorts, right? The different sorting algorithms, and so sorting is really, we have used sorting in convex Hall and closed pair problems. Sorting is really beneficial if you can sort your instances, or your inputs, your problem sets. It gives you lots of fidelity in figuring out the solution faster. So, and then the questions that are being asked in interviews are something to deal with sorting. Most of the time, like 99% of the time, it has to do with sorting, and then you take the brute force approach, and then you look at what are the options. Should I divide and conquer? Should I transfer and conquer, and so on? All right. So that's just one example I'm giving you here. The second example we're going to look at, which is very prominent in computer science, is computing a mode. And by definition, a mode is a value that has occurred most in a given list, right? So you're given a list and say, okay, what's the mode of this list, right? So in this question, according to this definition, what is the mode? What key is the mode in this question?
6.
Because it's repeated 3 times, right?
Yeah.
Because it's repeated 3 times. So we have 5 that is repeated 2 times. Then next to it we have 6, which is repeated even more, and that's 3 times. So the mode for this example, array A, is 6. Okay. Now again, brute force, right? So the question is, how would you go about finding the mode in a given array using the simplest algorithm methods that you can find, just the quickest that comes to your mind, and that would be the brute force. So I want anyone whose name is not Raid or Bob to just raise their voice and tell me how you would do that.
Does sorting help to like build a more efficient algorithm actually?
Who is asking, Bob? Okay, so
Yeah,
this is
sorry.
not. I'm just asking for brute force now.
Oh yeah, I know. I thought about the brute force, but like I was thinking like like does sorting help with like finding the most occurred finding the mode? It doesn't, right?
Well, you're jumping ahead. I don't know what the next slides are. I let you know in 5
Okay,
minutes.
sure.
Yeah. So I would like to have someone, maybe Alan Cho can tell us how you would solve this problem.
I would have 2 for loops like the last one. And this time 2 variables. I'm storing the count of how many times it was found in the array. And the other variable is storing the index. So you can point out which number is the mode after.
Okay, yeah, that's a solution there. So we're gonna scan the list and then compute the frequency of all distinct values that you find on the way. At the end of the day, we're gonna find the value with the largest frequency. So the way that we scan it, you possibly want to look into having a dictionary. I mean, this is totally fine. We are still brute force, but we have to, as Alan said, we want to have a couple of variables to help us here to keep recording. And if it was me doing this, I would have used dictionary. Dictionary. And dictionaries are extensively used in Python. It's just like one line of code that you can use for key pair values. So in this example, the data itself is the key, and the frequency is the value of dictionary. So we have key value pairs. We're gonna have a dictionary. Okay. So as we scan, we are gonna construct our dictionary. We're gonna add the key values to our dictionary, and we are walking through the list. We're gonna increment. So we're gonna have a for loop in here for I equals 0 going to n minus 1. This is n minus 1. This is 0, right? We are basically sweeping through this array. And then as we go through that array, we're going to look into the dictionary to see if the key is repeated. We're going to increment the count or frequencies here. And if the key is not repeated, we're going to create a new element in there in front of the dictionary. 6, it's being repeated. We're going to increment the count of it. 5 is being repeated. So in your algorithm, there, when you're searching, you have to search for the data. If you find it, you increment the value. If you didn't find it, you add it to the dictionary. Right? And so that's how you walk through the end. And so the catch here is that you're going to have an auxiliary list, right? You are having a new list. In my case, I have a dictionary. And once you have that, then you find the max in that. So in other words, you have to sweep this dictionary one more time to find which number is repeated most. Okay. Okay, so now it comes to the worst case. The worst case is a list with no equal elements. And we're going to compare the ith element of my actual list with the number of I-1 elements in the auxiliary, as I told you. And it appears that as we walk through it, for that auxiliary list, we're going to have 0 elements and 1 element, 2 elements. That's how we have to walk through it. And if you guys look at your cheat sheet from the first class, so this is gonna be giving you a sigma notation. That sigma notation will result in O(n) squared. I think this is like n minus 1 times n minus 2 divided by, if I'm not mistaken. Just check up on your data sheet from first class. So at the end of the day, that's going to be O(n) squared. Okay. And then so that's just for constructing your auxiliary list. However, you have to spend time for walking through the auxiliary list one more time, and that would be another O(n), because in the previous slide, once you have this, once you have constructed this list, you have to still walk through it, and that's another for loop to walk through this list. So that would be the time that's spent here. So you're gonna have to spend time for creating that list, and you're gonna have to spend time to traverse through the list. However, between the two, which one wins? This guy is growing in a faster pace because this guy is quadratic. The growth of this is quadratic. This one is linear. So between linear and quadratic wins. So worst case for computing a mode using brute force is O(n) squared. Okay. Right. So now the question is, we want to do instance simplification, pre-sorting approach, and how do we go about it? Most of the instance simplifications would use sorting 99% of the time. So the first bullet point you guys always put there is sort the input, and I give you 50% of the mark that you receive in your exam. That's a passing grade. You all have already passed, because in any question I give you, there are high chances that you have to sort the method, the inputs. And the second bullet point is after you sort it. So this guy is pre-processing or pre-sorting. Pre-processing. So pre-processing for the instance simplification is to sort the input. And after sorting, you will find all equal values are adjacent to each other. Okay. Now, how do we find the longest run of adjacent equal values? So let's say you've sorted the array, and then you find something like this. Right. So now the question is, how would you write an algorithm after you sort it? So let's say you bring in the merge sort or quick sort to sort your array. So for the first part, the pre-processing, you can only spend n log n. And then now the question is, how would you go about, looking for this? So how do you find the most repeated elements in a sorted array? How would you do that?
I think you would need to store the current most common element or the current mode along with like a counter for how many times that value has appeared, and then you just need a single for loop. And then you basically you basically check and see like how long the current run is.
Right.
And then you have like a conditional statement that reassigns the current max or the current mode to to a new value every time the mode.
Right. So in other words, we can do that in one for loop or while loop, and then if we can do that, that's on. Right. So I think for the last bullet point here, we're gonna spend on here because we only need one for loop to sweep, and then while we're sweeping, we're gonna look at the most repeated elements in that. Right. We are looking at the adjacent elements still in here, and so you see that with this instance simplification, our method for computing the mode of an array has been turned from a quadratic into linear logarithmic. I'm going to show you how. So we're going to sort and then find the longest run of adjacent equal values, right? So let's say we're going to use. I want to use a. So let's say we apply quick sort in here. Right. So we call a quick sort function in dash line. Then we're gonna set I to 0. And as Ray told us, we're gonna have a mode frequency. Right, so that's going to give us the highest frequency seen so far. And then the rest is walking through that sorted array. The rest, this while loop, is walking through the sorted array. Okay. So we're going to use I is 0 as long as it's not reaching to the end of the array. Do the following. We're going to have a run length. Initialize it to 1. We're going to pick the first element that's going to be run value, the 2 temporary variables here. And then we're going to have a check of the index. And we're going to have the check of the 2 adjacent array elements. So this guy here is basically checking the 2 adjacent array elements. You're going to compare these two, compare these two, compare these two, compare these two as it walks. It's going to do that. And so while you're doing that, if it is equal, I mean, this should be equal. I have to say this should be equal, right? If it is equal, you're going to increment the run length. And then if your run length is bigger than the mode frequency that you originally had, so this was your mode frequency that you originally had, you're gonna put that in your mode frequency, right? And if it is not, you're gonna come back to the basically to the while loop here. You're gonna increment the index there. Okay, so essentially you are going to adjacent elements. You're gonna compare if they are equal to each other. You're gonna add one to the run length here, and at the end of the day, you're gonna compare your run length with the biggest mode frequency that you have found. If it's bigger, you're gonna replace, and you're gonna continue going back to the main while loop in there. So that's essentially the method that's going to be used. All right. Okay. So with having said that, we're gonna look into the efficiency now. So the efficiency here is to bring in the sum of the time that's spent for sorting plus the time that's spent for scanning. So that's going to be the main execution time that's spent for completing a mode using transforming concur. And then, as I said, n log n, you're going to, let's say, bring the most efficient sorting algorithms, quick sort, or you can use merge sort. And then for the scanning, you're just scanning the array one time. So which one wins? One is linear. The other is the one is O(n). The other is linear logarithmic. Right, that's n log n. So this guy is growing faster than O(n). So for that reason, the computation time for computing a mode in this question is n log n. Okay. So that's how we do it. The secret sauce here was to sort your inputs. That was the secret sauce. Searching with pre-sorting problem is this is another question, right? You wanna search for a given key in an array, right? A key is given. Okay. So I cannot tell you that how much you love sorting. So again, stage one is to sort the array with an efficient sorting algorithm, quick sort. Or merge sort. Then apply binary search, right? So can someone tell me what was the time efficiency of binary search in big O notation? Do you guys remember binary search? Ben, do you remember binary search, Ben?
Was it O(n) squared? Binary search?
So the binary search was that you divide a sorted array into two pieces.
Log n, right?
Yeah, log n, exactly. So it was log n. And then the quick sort is n log n. So as it is for merge sort. So which one of these two are going to win between the stage one and stage two? In the worst case? So is log n bigger or is n log n bigger? Which one are bigger?
And log in.
N log n. So again, the time efficiency for finding a key can be reduced to n log n, whereas if you don't basically sort it, it's going to be n squared. Okay. There we go. Right. So I want you guys to look at the closest pair and convex hull problem and see if we use any kind of a pre-sorting method or pre-processing method, i.e., if we have tried to sort something in some direction, and if that's the case, I would say that hey, we use transform and conquer even for solving the closest pair and convex hull problems when it comes to divide and conquer applications. So look back to your last week's slides and see if you've used such methods to solve those problems. I think this is just the right time to stop here. That will cover the first topic of the day, which is about instance simplification, and I really expect you guys to understand it by heart, so that basically in interviews you should be able to use it. And it should be at the top of your head. It will impress the interviewer. That's a way to check you guys into the job market. I'm gonna take a rest for 10 minutes. So it's 6:54. Perhaps it's good for us to come back at 7:05, and then we continue our discussion for the second part of today's lecture. Thank you. All right, folks, we're going to continue our discussion for the second part of the lecture today. Hopefully, we can make it a, quite a straightforward lecture so that you guys can spend time studying for your midterm next week. So I'm not sure for next week if you guys want me to really be there. Because there are going to be questions to answer, and they're going to be between 60 minutes to 90 minutes to answer those questions. I could be available online, like in a Slack. So if you just in case if you have any questions, you could be posting your you could be posting your questions in a Slack. I would be happy to answer those. Otherwise, I don't think that I need to be like standing here just do nothing watching you guys, because I'm pretty sure you guys can take care of yourself. So I think for the midterm next week, you come in at 6 o'clock. You take the midterm from D12. You start writing it. Most of the questions are going to be like algorithmic questions to deal with writing a sequence or a pseudocode. I'm not expecting you to do an actual implementation, but you're more than welcome if you choose to like implement the algorithm in Java, Python, C, or any popular languages that you wish to do so. Are there any questions for the midterm next week?
You said
Sorry, go ahead.
You said there's going to be 4 questions. Is that right?
Right. So I tried to pick from the topics of every chapter, and then give you one question from each chapter.
Okay, so 6 then.
Right. So the first chapter was So I think it's 5 maximum 5 questions, because midterm is 20%, right? If I can recall, I have to look at my records for how much it may be in the final, but I think it's 10 or 20% of your final mark is going to be your midterm.
So you didn't take any questions from chapter 1?
Chapter 1 is, what is it? Let me just look it up, because I don't want to say something that is not true. Yeah, so chapter 1 is mostly introduction to what's happening. I don't think chapter 1 is worth a question, to be honest with you. It's just very brief introduction to all different type of algorithms that are being investigated throughout the rest of the book. So in my opinion, you should be able to still skim it, but I think the main topics are going, the main activities are going between chapter 2 and 6.
Okay. Thank you.
So can you hear me, first of all?
I can hear you, but I cannot see you.
That's deliberate.
Yeah.
Okay.
That's a classic
now?
problem, hey?
Can you see me now?
There we go. Yeah.
Okay. So can we do the midterm electronically, or do we have to write it on like a piece of paper, then scan the thing, which takes like 10 to 15 minutes of like...
Oh, you never have to scan anything. I'm going to give you questions in Word document, and then you have a chance to type it.
Yeah, or like use electronic pen on top of it.
Yeah, that's fine. That's fine.
Okay, great.
Yeah.
Thanks.
Yeah. Okay. Someone is looking at... All right, so let's get it started for the rest of our presentation today. Okay, so the other way for transform and conquer second class. There are so many classes, but I'm just giving you. So this class, this course is just introduction to algorithms. To be honest with you, we are only covering like 10% of the landscape. I'm just covering the basics. So it's nowhere close to where the state of the art is, but it's just basically putting the foundation for understanding how the algorithms are working underneath, and everything boils down to the topics I'm covering in this class. So when it comes to topic of transform and conquer, the two main ones are instance simplification and rep change. And then I already talked by giving you some examples of how you can treat pre-sorting. And the main solution there is to sort it. You're giving a number of inputs, you sort it, and then once you sort it easily, you can do a binary search or any type of different methods to look for what's being asked for you. The second topic or second type is rep change, representation change, and then what comes really outstanding in rep change is the heap, the notion of the heap, and the heap sort. So these are the things I'm going to cover right now. The idea is given an array, we want to transfer it to a new data structure. So you are given a type of data structure, in this case an array, and for getting to your answer in a faster form, you transform it to a different form, different data structure. And in this lecture today, we're going to transfer the arrays into the heap, the type of heap. And the reason for that is if you want to manipulate an array list as a heap, it's more efficient. Okay, that's the catch. Okay, how it's efficient? The insertion and deletion of an item from a heap is efficient, and you see that that's of O log n. So instead of it being quadratic or linear, it's even less than that. It's logarithmic. It's quite fast. Heap definition. Okay, so we are going to talk about heap. What's the definition of a heap? It's like a binary tree. I covered the binary tree in last class, except that all levels are filled. The last level where the leaves are, you want to fill it from left to right. So you want to make sure that if it's a binary, the root is always bigger than the children, which is the case here. And then at the end of the day, you're gonna look into the leaves, and you're gonna complete the leaves from left to right. So left to right. Complete leaves, or put leaves from left to right. Okay. So as you can see in this figure, this is like a heap. This tree is a heap. So I'm just giving you some examples. I have 6 different instances of a tree, and the question is which one of these are heap, which one of these are not. So let's look at the first one, right? The first one, A, right? So if you guys say that this is a heap, please raise your hand. And if you're saying it's not a heap, please do not raise your hand. 2 people, 3 people. Bob, Ray, Midi. Who else is saying that this is a heap? The rest are losers. So it appears that the losers are winners here, because I said that the leaves should be filled from left to right. So in this case, we have a leaf that is filled on the right wing, and so for that reason, this is not a heap. Okay. The property of a heap is that if you look at the leaves, it should be filled from left to right. How about the second one? Number B. Sorry, item number B. So item B. Who is saying that this is a heap? Raise your hand. No. Okay, so Inadi, can you tell me why you think that this is a heap? I cannot hear you.
Can you hear me now?
Yeah.
Okay, so initially we have the root node, then the left and the right node is taken, and then the children of the left node, both is left and right taken. So that's why it follows
Right.
the heap.
Okay, so that means one condition. The other condition is the binary tree condition, and that condition is the root should always be greater than the children.
No, I thought the heap requires like the left side to be filled first, then the right.
Yeah, so that's one. So if you go back to the previous slide, there are maybe I missed that. So there are two conditions, right?
Oh, sorry.
That's the first condition, which you're correct. And the second condition is every parent is greater than or equal to the child. That's the second. So you have to meet these two conditions to have a tree to be of a property of a heap.
I see. Okay.
So if you go back here, here you see that things are okay, but things are not okay here. Although, yeah, the first condition is met, right? The leaves are filled from left to right, but 5 is not. So this guy is a root to 7, and 5 is less than 7. So that property is not met. If this was 7 here and 5 was here, yeah, then it would have been a heap. Okay. So this guy is not a heap. Right. And then the next one, this one, it's obviously a heap, right? Yeah, because everything is left to right. That's okay. And then all the roots are bigger than their leaves, right? All the roots are bigger than their leaves, so this is a heap. Okay. D. This is not even level because first there are a few problems here. The first one is that this guy should be here, right? The second problem, these two also should be placed here from left to right. So this is not a heap. What is wrong here?
There are 4 levels, and level 3 is incomplete.
Right. There is one more problem.
6 is smaller than 7.
Exactly. So this guy first of all should come here, 2 here, and then these two should be placed. Okay. Last piece. Obviously, it's a heap because all the levels are filled, and then you go to the next level. They are doing from left to right. That's correct, and all the roots are bigger than the children. So we're all good here. So in these 6 examples, we have 2 trees that of property heap. All right. Okay, so we're going to use this property and see how we can take benefit from it throughout the rest of the lecture today for solving algorithms. So if you do that, you will eventually find out the maximum element is in root. Okay, so obviously the maximum element is in root. And what you have to memorize is there's a notation for finding the height of it. So number of inputs you have is the floor of log n. That's going to be the height of your tree, of your heap tree. So this is level 0, level 1, and level 2. we have 1, 2, 3, 4, 5, 6. So that's going to be log 6 base 2. That's the floor of it, and that's going to give us 2. Okay, so if you compute it, you put the number of inputs, and you calculate log input base 2, and that's going to be the height of your tree, of your heap tree. That's level 0, level 1, level 2. Do you guys get a chance to watch the platform movie that I was telling you? No one watch it?
Yeah, I watched it.
Did you like it?
It was kind of brutal to
Yeah,
the
it was.
end. Yeah, but I really like the how they demonstrate the class system.
Right, exactly. Yeah, it's kind of ironic to what we have, in the capitalism world. So
Yeah,
It's pretty much like
I come from mainland China, so I also kind of feel
yeah,
that
you
too.
can attach it to that.
Yeah.
So yeah. Okay, that's great. At least I have someone to impress me here. All right, going back to our discussion. So that's the height. That's how we find the height of a heap. Let's continue with that, and then what am I trying to say here? Oh, okay. So there are more rules as to where we have to put this, and basically how you want to represent this heap as an array, right? So you are given an array. You can restructure it and put it like the way you do sorting algorithms, and you sort an array to solve problems. You can basically process an array to look like a heap, and then you process it accordingly. Use the benefits that heap will bring you to show you how we can use those benefits. So if you're given an array, the way you have to order it is that the rules are this: the parent of a key in position I will be in position floor I divided by 2. And I tell you how I do it. So this guy is in position 1, then the floor of 1 divided by 2. Floor of it. Is 0. And then we're gonna read from left to right. So this is gonna be 1. Then from left to right on the second level, it's gonna be 2. To right 3, and then 4, and then 5, and then 6. That's how things are gonna be put into the array that we look or represent a heap. And then we're gonna disregard the first element. So we're gonna put the first index, which is index 0, away, and then we're gonna fulfill the rest of the array by starting from the top, and then start marking, 1, 2, 3, and then left to right to the next level, and then fill up the array indexes. That's how we're gonna do that. So if you do this, you are going to find the relationship of the relationship between the array itself and the tree, and these are the relationships. The left children of a key. So let's say key. So let's say this guy. This guy is a key. Okay. So this guy is key at index 1, key 1, right? So what I'm trying to say is this guy, key, right? So this guy is 9. We are looking at root, the main root, this guy, right? The index of it is 1, right? The position of the left index is at 2i. 2 times 1, which is 2. Okay, so you see that the position of the left, and this guy is the root, is at position 2. Okay, and then the right children of a key I is at 2i plus 1. So again, we have key 1, this guy, right? Key 1 is 2 times 1 plus 1. This is 2 plus 1 is 3. That gives you the position of the array that you have to put. So 3 is here. So you're going to put 8 into position 3. So that's what the calculation is for translating the heap tree to its array. Okay. If you're looking at the tree, by just looking at it, you just say from left to right. At every level, from left to right, you just put it there. If you're programming it, you have to basically implement this. So if you're programming a heap in any language, programming it in any language, you disregard the first index, and what you're going to end up with is basically this. You're gonna construct that array that has these properties. All right. So once you do that, that gives you this array, and this will represent a heap. Okay. All good. Do you guys have any questions so far? So we talked about the height, in the previous slide. So we talked about the height, how you define the height. How you find the height is it's a floor of log n base 2. And then we talked about the translation between the tree representation of a heap and its array. Okay, this is what we're trying to do. Okay. So example, what is the array representation of the following heap tree? If someone raises, so first of all, is this a heap?
Yeah.
Yeah. Why it's a heap?
Because it satisfies all the conditions. The biggest on top, and as you go down, you can see everything's in order, and also it's filled from left to right.
Right. So now the question is, if it's a heap, then what is the array representation of this heap?
Is it just 10, 8, 7, 5, 2, 1, 6, 3, 5, 1?
Exactly, because the way if you're given a tree of it, you just look at the left to right at every level, and you just write it down. So I just look at it. I say the first location, nothing here. 1, 2, 3, 4, 5, 7, 8, 9, 10, 8, 7, 5, 2, 1, 6, 3, 5, 1, and 11. Okay, there we go. That's it. So you can quickly translate a tree of a heap, of a type heap to its array representation. And one interesting point that you see, you will find that all of the parents are standing on one side, and all of the leaves are standing on the right hand side of that array. That's another interesting point that we find in here. Parents on one side, and the leaves are on the other side.
Sorry, I have a question.
Bob, yeah, go ahead.
Yeah. So how do you exactly know if it's filled from left to right? I can't miss out on that part.
Yeah. So we go back to the rule, right?
Yeah.
The rule is that we look at the index of the parent, right, and the index of the main root starts from 1. We don't have 0, okay? As you see, I marked 0 to be none here. So the first place is 1, okay? And so that's where the starting point is. That's where the starting point is.
Okay.
So you see that 9 goes to the first location. So if you're basically if you're translating a tree that has a heap property to an array of it, you have to write an algorithm that meets all these 3 bullet points.
Okay.
So the first element goes to the first location, and then from there you decide what the left children should go and where the right children should go. So the left children go to index 2i, and the right children goes to index 2i plus 1 from the parent of it. So the parent is at location 1, so you say key 1. So 9 is at key 1, and I want to say where the left children of it should go. So I have to say 2i, right? And then 9 is at location 1, so it's 2 times 1 equals 2. So that means that the left children of 9 will go to index 2 in that array.
Okay.
That's how you should do that.
Okay.
Which is correct. 5 has gone here, right?
Mm.
You do the same for the right, and you do the same for the rest of the tree.
Okay. I see what you're doing now.
Yeah.
Okay. Thank you.
Yeah. Please just write notes here, because I'm pretty sure you guys will. Even if I come back to it like next year, I will have to say, oh, what is this? So please write a note. I'm pretty sure you guys have to, somehow write some hints here to memorize it, or to remember it, recall it. Okay, that's good. So we have that, and then the interesting part was that the parents are standing on the left side, the leaves are on the right side. Oh, there we go. Okay, so the exercise here is the tree representation of this heap. So we know that this array is a heap. Okay, it's given to you. It's given part of the question. We know that this is an array that represents a heap. Can you guys represent it in a tree form? So whoever solved this first, just raise your hand, and perhaps you could share your handwritten tree in front of your camera, so I can see that, and the class can see that. Maybe Yutong can answer it. Yutong Lee or Navneet.
Sure.
Or Kathy. I'm impressed that Kathy is sharing us her camera today. Thanks for sharing your camera. So whoever has sorted this out, please raise your hand. And no, anyone other than Raid, and other than Enadi, and other than Bob. Yeah, if you come up with the full tree, please raise your hand. This should be quite fast, right? I mean, heap is a kind of a binary tree with the properties that the root is always bigger than the leaves, and you're gonna start filling up the leaves from left to right for each parent. So Kathy, can I see the implementation? Come closer, closer, closer. So 17, 11, 12, 9, 8, 10, 5, 1, 4, 6. The last leaf on the right is 7, right? Okay. Okay, yeah, that's correct. So if you want to present it as a tree, it's going to be 17 at the top. You know, you're reading things from left to right in that array. That's the first index. And then we're going to have 11. It's a binary tree, so we're gonna end up having 12. And then we have to start from left to right again. So it's going to be 9, 8, 9, 8, and then we're going to have 10. We're going to have 5, 5, and then we're going to have 1. Again, we go to the next level. It's a binary tree, so we're going to go to the left, 1, then 4, 6, 2, then 3. Last but not least, is 7. Okay, you guys all got this? You're all good? Okay, so that's how we did it. Just practice to interchange between the tree representation of the heap and the array of it. Yeah, you're all good. All right. And we go the other way. Obviously, there are no need for 10 minutes. I can draw the array representation of this heap. So can someone, maybe Ben, can you just tell me in sequence what is the array representation of this heap?
Would it be 24, 13, 17, 9, 6, 11, 15, 5, 7, 2, 4, 10?
There we go. Okay. So, it's quite easy peasy. Right. So now we want to see how we can take benefit of this structure that is called heap, and then what's the purpose of it and how we can solve problems. So the first thing that is interesting here is the insertion. So if you have a new element that is coming to this array or this tree, what we're going to do is we have to create a new leaf and put it to the next available leaf in that tree. And then the second step is to heapify. And the heapify means that we have to bubble it up such that that new element is going to be placed in the right location of the tree or the heap array. So this is how we're going to do that. So let's say we want to insert 17 into this heap. So this is a heap, obviously. All the elements, all the roots, all the parents are bigger than the children, and everything is filled up from left to right. The array representation of it is as you can see. Now let's heapify and insert the 17 here. So once we're gonna insert 17, we're gonna add a new item and we're gonna place 17 here. We're gonna add a new element and we're gonna place 17 here. This will then change the property of the heap to be a heap, because it's not a heap because 17 now is bigger than 7 and 15 and 16, although we have placed it at the right location, but that node is bigger than all of them, and so it's just gonna refute the property of a heap. So we have to bubble 17 up to place it at the right location. We have to heapify. It's called heapify. Okay, it's called heapify. So let's see how things are heapified. Let's see how things are defined. The way we do that, we do replace with the first direct parent. So we swap it, okay? And then we see, is this a heap? No, it's not. So we have to heapify again. We do another replacement. We pull 17 up. We swap 17 with 15. Is this a heap? No, it's not, because there is 16 here that's even smaller than 17. So last but not least, we are going to heapify. So can someone tell me how much time is spent to insert this new element into a heap? Do I need to scan the entire array to find its location to keep the property of a heap?
Is it log 2n?
Exactly. So you are spending log n base 2 to heapify and put the tree back in order, or the array back in order, where the properties of a heap are still meeting, right? Yeah, log n. Okay. The height of the heap is log n, so the efficiency of insertion is log n. All right. The next property for a heap is delete max from the heap. So the way we do that, the max is at the top, right? The max is always at the top. We exchange root with the rightmost leaf. That's the rule. That's how we want to delete it. And then we delete that element and heapify. So I'm going to show you an example. So the question is, you're given an array and you're looking for a max value in it. The way we want to do that, we can turn that array into a heap, an array of type heap, and then we delete the max from it. So the max is always the parent, the topmost parent. So this is the main root. Is always the max. Right? So the way we do that, we're gonna replace it with the rightmost leaf. Okay, we're gonna do that. Right? These two are replaced. And then we're gonna delete this guy. Okay. Now we have to heapify again because 7 is smaller than 16. So we do that swap in there. And now, when it comes to comparing these, we have two numbers that are children to 7. So which one do we have to swap? Which one do we have to swap? And the answer is the bigger one. So when it comes to saying two children that are both bigger than a parent, you swap the bigger one. So we swap 15 with it. And I think the problem is solved. We have the heap again here. So deleting max, what's the computation time here?
Also log n.
Log n, yeah, excellent.
Yeah.
Right, there we go. So the catch here is that you are given an array or a tree. You can easily turn it into a heap, and then you spend only log n to delete or insert an element into it. Okay.
I have a question.
Yeah, go ahead.
How are you finding the indices of like what you were swapping? Because I was trying to use like the parent of the key in position I, like the floor of I over 2, and I kept getting off by 1.
Oh, that rule is only applying for anything that's bigger than 2. So if you go back, So you see that there is a condition that you should start.
Oh.
So it's not applying to the first one, because the first one is always the first, right? The first one always stays at the first location. So that's why the condition is made there to make it the correct computation. Yeah, that's a really good question. So this condition should be met. For the first one, I has to be between 2 and n. So we start from these guys, the intermediate or the middle parents,
Can we go to where we're trying to delete 17 and just kind of go through it a little bit more slowly? Okay, so we have an array of length, what, 9? There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we now have an array of, okay, sorry, 0, 1, 2, 3, 4, 5, 6, 10. All right, so it's an array of length 11 now. And in order to find the index of what should be the parent, we do the floor of, is it 10 over 2 or 11 over 2? I guess they're both gonna end up being 5, right?
Well, I haven't. I'm going to show you how we construct a heap. So
Okay.
So let's say, so once you add 17, you can, to be honest with you, you can add 17 anywhere, because this is an array. Arrays it's like a FIFO or a queue. So you're adding 17 as a new element to a queue, or in other words, in a list. So you're given a list, you're adding an element to it, and now you have to give this this array, because you don't know if it's a heap or not, right? Now you have to apply a function called heap, and you're gonna heap A and have a new A, or a new reference to A. So that part I'm gonna go and cover it in the next slide. So let's see how we can do that, because I was just telling you how we do the deletion, just a visual representation how we do things in here. Okay. So the first thing we do is initialize the structure with keys in order given. So that's obvious, right? Starting from the last, which is the rightmost parent node, fix the heap root, add it. So if it doesn't satisfy the heap condition, so we have those two heap conditions that I just gave you. Keep exchanging with the largest child. I just told you that you have to do the exchange with the largest, right? If you have two children that are bigger than the root, you have to exchange it with the largest. So you can easily program that. And you have to go back. So this is like a recursion, or it can be a for loop, right? This is a for loop. Go back to step 1 for preceding parental node, right? So, right. So I have an example in here, right? 297658. This is given to me. And I have to start. So let's go back to the algorithm. Initialize, that's what we've done. Then we go to step 1, start with the last, which is the rightmost parental node, and fix the root, fix the heap rooted at it. If it doesn't satisfy the heap condition, keep exchanging it. So we start from the rightmost. In this case, the rightmost is 8, and we compare it with 7. Okay. So I think for you, you have to say this is 1. So just go back to your question. This is 1, and then from here, this guy is 2, but this guy is the parent to these two, right? So So 2 is the parent to 3 and 4. I think that's how you should be marking it when you're programming it, right? And then you have a chance to go for, you know, then you have 2, 9, 7, and then you have so 2 is the parent for 9 and 7, and then you say 9 is the parent for sorry, 6 and 5. I made a mistake there. So the parent for 6 and 5. So 9 is a parent for 6 and 5. And then 7 is a parent for 8. Okay, so you have your leftmost, there are parents, the rightmost are the leaves. Okay, 6, 5, and 8. These are the leaves. Okay. So once you do that, then you have to do start from the rightmost. Okay, and rightmost is the last leaf in here, which is 8 in this array. So in this array, the rightmost, you always pick the last one. So you always pick the last one, and you find you find what is its parent. You can find that. I gave you the formula for it. So I gave you the formula. If it's the left wing is 2i, if it's a right wing is 2i plus 1. So this is the left, this is the right. So the root for this is L over 2, and the root for, let's call it parent P. P. And if it's the right wing, it would be right wing minus 1 divided by 2. Right? You can kind of reverse engineer it that. Or you can, I'm just showing it by trees so you can visualize how things are happening. And perhaps you can do the same with, when you want to really implement one of your favorite languages. So what we do here, we go to the rightmost, and the rightmost is the last element in the array that's given to you. We compare it, we find its parent, we compare it with the parent. If the parent is smaller, we have to do swaps. That's what's happening here, right? And then we go to the next one. The next one is 5, right? We do the same thing, right? And so 5 comes here. Oh, sorry, this is correct actually. We don't have to do any swaps here because 9 is bigger than both of them, right? So we don't have to do swaps. So we are okay here. We are okay here. Then we have these guys. Then we go one level up. So this level is taken care of. We are okay here. And then now we are going to this level, right? And then it's kind of recursive call. So now we have to find the comparisons of the rightmost 8 with 2. Okay, so 8 comes here, 2 goes there, and then you go 8 and 9. So 9 comes here. Oh, sorry. The rule was that you have to pick the biggest one. So you have 2 children. You have 2 children, 8 and 9. Both of them are bigger than 2. And if that's the rule in your implementation, you have to pick the biggest one. So in this case, 9 is bigger than 8. So we have to swap 9 with the 2. Okay. So we swap that. This will stay. This will stay. Then we are doing one more round because 2 is smaller than 5 and 6, and then we have to pick the biggest one. So it will be swapping with it will be swapped with 6. So that will give us a heap at the end of the day. So we go one level up, and then again we have to sweep it back down. All right. I don't think if I'm expecting you guys to implement heap. I believe that there's a bunch of libraries in Java that can do heap for you. So you just easily give your array and it give you a new array that is a heap. Okay. But I just want to make sure that you guys understand. So in the exam, I'm going to give you such examples that hey, this is an array. Start to heapify. I don't want you to implement anything if it's a question in the exam. Are there any questions? You're all good? You guys all got the point?
So you said on an exam, we're not expected to implement, so just provide like pseudocode? Is that what?
Yeah,
Yes.
yeah,
Okay.
yeah. All right, good. So step 0. Yeah. So you have to make sure that you always swap the largest children, the largest child with the. So if you have, I think the catch here that I kind of was being misled here was that when it comes to comparison of the two children with the parent, you always have to see which one is the biggest to do the swap. So that's one of the key points here. In this case, 9 is bigger, so that's why you have to swap 2 with 9, not 8. All right. Navneet, are you okay? You all good? Well, we
Yes.
cannot. Okay. Okay. Good. Good. Let's move on. I think so. This is a good stopping point. I think the last piece I want to cover, and that's going to take benefit from the heap properties, is heap sort. So this is going to be added to. Oh, I see 2 cats in 2 different frames, and it's going to be added to our sort list. So I think you guys learned about insertion sort, bubble sort, merge sort, quick sort. What else? And then heap sort is one addition to our sorting algorithms. Sorting is really important in algorithms. Obviously, 90% of the problems can be solved by sorting something, some level of inputs. So let's take 10 minutes of a break time. It's 8 o'clock. We come back at 8:10, and I'm gonna present you the last piece. Thank you. All right, everyone. Let's cover the last piece of the lecture today, and I'll let you go afterwards. So obviously we covered heap, and so there are several benefits to it. One of the main ones that is so obvious is the heap sort. That's based on the construction of a heap here, and that's going to be the topic of the last topic of today's lecture, is to discuss the heap sort. This was discovered in 1964. So if I want to basically give you some background, there was the quicksort who was discovered, which was discovered by Hoare in 1960, and he's Hoare is a computer science scholar. He got the Turing Award for it, and then Williams discovered heap sort based on the idea of how you can construct a heap. And this is how it works. We basically construct a heap for a given array. So we turn the array into a heap. So let's say you have an array, and you guys can find a bazillion number of different APIs and libraries for a function that is a heap function. So say heap A gives you a heap array. Then you apply the root deletion operation n-1 times to the remaining heap. I'm going to let you know how we can do that. Okay, so we're going to cover how we are going to do that. And then last but not least, we're going to go and repeat the operation. We're going to go back to what we do, construct a heap again, and we apply item number 2, and we keep doing it. So before we continue here, can someone tell me what is the benefit of having a heap, or what benefit heap brings us that we can take advantage of it to sort an array in descending order? So can you guys think that how heap is represented as a tree, and what benefit from that tree you can take to construct a sorted array in descending order? Any thoughts? Anyone just want to throw something?
Well, because it has the max on top of it, so if you want to sort it, like descending is largest to lowest, right?
Exactly,
So,
right. So yeah, that's I mean, you can construct a heap the other way, but this in this class I'm just talking about the max heap. And max heap means that you always keep the max at the top, at the mother parent or the main root, and once you pick that, then you heapify, and you pick it again, and you pick it again. That gives you the order of descendants for sorting array, right? You can pick those. So this is how I can show you. Let's go to the next slide, and that's where exactly the main the main algorithm is happening. So you have an array that is 297658 at the top. This is an array that's given to you. So the stage 1 is to turn this to a heap. All right. So I'm gonna write it down, and let's see how we can do it together. So 2, 9, 7. I suggest you guys write as I do. 6, 5, 8. Okay, so let's assume that we want to put this into a binary tree. So we're gonna do 2. Oh, this is too short of an edge. So we're gonna do this 2, and then we're gonna do 9, 7, 6, 5, 8. Right? We're gonna represent this as we are representing the heap tree, right? And now we're gonna turn this to a real heap. So we have to turn this to a real heap. So what we're gonna do is we're gonna, I gave you the algorithm. We're gonna start from the leaves, from the rightmost, and then we're gonna go back up recursively. So we're gonna swap these two because 8 is bigger than 7, right? So it's gonna give me 2, 9, 6, 5, 8, 7, right? We already swapped those. Then we go to the rest of the leaves. We compare the rest of the leaves with their parents. Oh shoot, I lost it. So I'm gonna. Did you guys draw what I drew? So we're gonna do the rest. 2, 9, 8. This is what we left off. 7, 6, 5. Right? It was 6, 5, right? And then we're gonna do to the rest. So we already did this swap. We already did this, and then we're gonna go to the rest of the leaves. Do we need to do this? Do we need to do this replacement? That's a question mark. The answer is no, because 9 is already bigger than the leaves. So we already have this guy 2, 9, 6, 5, 8, 7. So we're gonna go to the next level. So we have this level covered. Now we're gonna go to the next level and then do the comparison here and here. You guys see my handwritings? Yes. Okay. So we're gonna go to comparison between the next level of the parent, the root parent, and the children 9 and 8. And so when it comes here to swap 2 with 9 or 8, we have to pick the biggest one. And in this example, we have to swap 9. So 9 comes here, 2 goes here, 8 stays, 7 was as it was. You know, we had 6 and 5, right? And then the last step is so this guy is at the right place, this guy is at the right place, this node is at its right place. The only problem is the left wing, right? You see a problem here, we do a comparison here, we do a comparison here, we pull up the bigger one. So we have 9, the bigger one between 6 and 5 is 6. 2 goes here, 5. Done. We have a heap now. So you either have to write a function to do this, or you can, basically find an API in Java or any of. I think Python has a bunch of libraries that you can just easily use all these different sortings and heaps, and, all these different data structures that you can use, and it gives you a heap at the end of the day. So your initial array was what? Just trying to recall. You guys just write this down on your notebook. you are homework, but later you can just check it. So this is the final. And what was my unsorted? What was my original array? So the original array I had was something like this. I had an array that was containing 2, 9, 7, 6, 5, 8, and I gave it to a function called heap a, and give me a new array, and the new array is 9, 6, 8, 2, 5, 7. Okay, from left to right. 1, 2, 3, 5, 6. Are we so far so good? You guys all get it? Okay, that's what the translation happens, right? So that's essentially your function. That's what it does. Login.
Wait. Are you saying the worst case scenario for constructing the heap is log n?
For every step, yes. So for every step, you are basically swapping something with something else, right? And you have to do that n minus 1 times, right?
I don't understand it.
Well, the steps that I was drawing, at every step you have to pick an element and do some swaps, right? And because this is a tree, this is a binary tree, you are pulling up that element to the top or bottom. You're doing some swaps in there. You're working on one side of a tree, and that's a log n, right? So because you cut the tree in half, right? It's a binary tree. So every time you do that, it's a log n efficiency. So you don't have to check for comparing it to all elements in your array, right? You have to just basically play within half of the array, half of the tree essentially, because let's say, let me just draw something here. So let's say we played with this guy, we brought it up or here, or I don't know, we had something like 2 here, that was here, we pull it down. So you're always working with half of the array, and that means a log n for every step.
But I thought, okay, so if we're constructing the heap, I thought the worst case scenario, just using this as an example, what if we have to swap like something between like 6, 2, and 5, and then also swap 8 and 7, and then also swap one of the 6 and 8 nodes with 9. That's 3. Then we have to go back down. So then couldn't we have to do it another 3 times, which is 6, which would be n?
Right. So I think the missing part is the n. So we have to do that n times on the worst case, because we have n elements in our array. So it could be O n log n. That would be the right solution, I would say. I was just trying to infer that for every time that you're doing the comparison, because you have to work on one side of the ring, you have to do log n base 2, and then because you have to repeat it for n elements in the worst case every time, and that would be n log, linear logarithm.
Okay.
Good.
I think so. Is it?
Yeah.
Is this is for the construction?
This is for the construction, exactly. Yeah, this is for the construction. So on the worst case, the construction is that you have to heapify all elements. That's n, and every time you do that, it's log n because you're dealing with half of the tree.
I get it.
Right,
yes, yeah. I get it. For each element, it's log n.
Yeah.
And then you have n elements. I got it.
Exactly,
Okay.
yeah.
Sorry,
Yeah.
I get it.
Okay, we are all good. Everybody else is understanding this. So the plan here is to have a function we heapify. you're given a random array, you turn it into a heap. Now go back to the slides. You guys took a note of this for a picture? Yes? So let's go back. Okay. So basically, that's what's happening on the left side. And that's what I just showed you. So we're going to end up with this array, that's a heap at the end. And now the catch is stage 2. Stage 2 is to pick the root, which is the topmost parent in the tree. So, 9, 6, 8, 7. Right? We had this. Then we know that this guy is the maximum because it's sitting at the parent at the very top. So we pick that. That's the first element in our sorted array. And that's the secret sauce here. So we pick this guy. So how did we do deletion? How did we do deletion in a heap?
You
Yeah.
you switch it with
with
you take
the right
9.
with the rightmost. You take
Yeah.
7.
So yeah, you
You
switch
take
with 7.
9 exactly. So you take 9 and then you switch it there, right? So you take 9 and then you switch it there. So 9 comes to a leave. Sorry,
Yeah,
to a leave,
you get rid of
and then
9.
you pick it out. So that's what's happening here. And then you have you swap it, then it comes 7, 6, 8, 2, 5. So 7 comes here. So that's 7, 6, 8. No, you read it like that. 7, 6, 8, 2, 5. And 9 comes here, and then we pick 9 out. So the entire thing here is gone.
Yeah.
You guys get the idea. Now we have a new heap or something that we want it to be heap with 7, 6, 5. 6, 8. Eight, 2, 5. Okay, so now the catch is to do the heapify thing again, and that's what's happening at this stage. So if we apply heapify, we get this 8. We do the swaps here. 6, 7, 2, 5. Right, and then we have to basically do the swaps again. We swapped 8 with 5. The last level, rightmost wing. It comes to here. We take the 8 out. It comes here. We take it out. So we already have 9. Then we have 8. So if you guys continue doing that, you're gonna take 7 out, then 6, then 5, and then 2. So that's how things are gonna be ended to be sorted as a heap sort from an unsorted array using heap to a sorted array. And that's how heap can help us in this process. So the first stage is to make a heap. Second stage is to pick the last one. Then you could go back, you make a heap, you pick the last one, make a heap, you have to do it a couple times. Okay, so for every time it's log n that you're picking, deleting an element. So every stage of deleting an element is log n. So Right. You guys see the sequence here? Are you taking notes? Just to make sure you recall it later. It's quite intuitive, right? You just have to follow the steps. Okay. Okay. So once we do that, build a heap from a given list of arrays. That's n log n, as we discussed with Ray, right? And then repeat the operation of root removal n minus one time. So that operation of removing, we have to do it n minus one times. So at the end of the day, we're gonna end up with O n log n in terms of computation time of heap sort. Okay, so it appears that heap sort, we can do it in place. It does not require any storage. If you guys remember, we did this quite similar to what was happening with quicksort, whereas with merge sort, we needed extra space. Just go back to divide and conquer slides to take a look at the merge sort. So we had merge sort, and that was n log n. So that was a divide and conquer. And then we had quicksort, n log n, and then this one is heap sort. So it's in that category. So if I want to show you, matrix of what we've learned so far in terms of selection, bubble, insertion, merge, heaping, I think these are the key sorting algorithms that you guys must know to pass an interview. If you guys want to be successful in computer science department of industry, you have to know all of these. You have to memorize it. Perhaps just prepare it for your interview. I don't care if you forget it after the interview once you got the offer. Perhaps you could write an email to tell me that you passed the interview and how grateful was that sorting instruction. So we had the selection sort. We saw that the best case, worst case was n squared. I've already provided the matrix for in place. Yes, it is in place. The only thing that is not in place is merge sort, as I have told you, as we have discussed in the divide and conquer. So merge sort is not in place. The rest are in place. And if you want to put things into one category, I would say merge, heap, and quick goes into one category. Bubble and insertion are linear, and selection is quadratic. So selection is the worst, bubble are medium, and merge, heap, and quick are the best that you can approach. Right. So if it was me to pick one sorting algorithm, I would always go with quicksort. 1960. Go back to 1960. Just search for this thing. And interestingly, this guy was shooting for a bubble sort, I guess. And while he was solving for bubble sort, he found a quicksort. So and it takes time for people to come up with these algorithms. It can take 30 years. He spent the entire life to just figure out the quicksort. So don't think that these things are coming by intuitively or heuristically. People really spend time on finding ways out, and people write PhDs about sorting algorithms. So if you come up with a sorting algorithm, I would say that you could apply for a Turing Award, which is the most prestigious award in computer science. There are some new sorting algorithms. It's just for your information. It's called counting sort. You could Google it, radix and bucket sort. I don't know, this can be Bob sort, or there can be Ben sort or Medi sort. So just see if you can come up with your sorting. I doubt it because nothing can beat n log n to date, but I think radix sort appeared to be a linear approach. Just check upon it. I was reading an article about that. So there are different sorting algorithms that they use. They benefit of the memory construction and cache data structures to basically come up with a better computation time than n log n. Okay, so that should conclude our session today, except for, I think since we have time, let's go on a slide number 55 for the first exercise. Consider the problem of finding the smallest and largest elements in an array of n numbers. Design a pre-sorting based algorithm for solving this problem and determine its efficiency class. Right? So let's spend, I don't know, 5 minutes on, so the question I'm going to give you in the midterm and final exam and quizzes is going to be of this nature. I'm just going to give you, okay, this is the problem, and how would you go about solving it using transform and conquer, in which you have learned simplification methods and some instance transformation methods. You know, I introduced you 2 methods, so you have to think and be able to basically find how you could be solving such problems using transform and conquer. So I give you 5 minutes. It's 8:40, maybe at 8:45. I just call out one of your names, and you should be able to tell us how you would find a solution to this problem. Okay, just spend 5 minutes to solve this. You got 2 minutes, and I'm gonna call out a name. Okay, so I would like Youngju K to provide us his answer, and perhaps we can have a discussion based on that.
Do you hear me?
Yeah, I can hear you, but I cannot see you.
Give me a sec. Yep, do you hear me?
Yeah, go ahead.
Because it's pre-sorting based algorithm, so I'm going to merge sort the list, the array first. So
Right.
it'll be n log n.
Yeah.
And I'll pick the first index and the last index as the smallest and largest respectively. So just constant. So it will be just n log n.
Oh, this is fantastic. So did everyone could relate to the solution? So you basically, when it comes to pre-sorting, that means kind of pre-processing. In other words, 99% of the time you have to sort the input. So in this case, you are given some random, array or random inputs, some numbers in it. The first thing you do is you apply pre-sorting. That means that I'm going to do whatever, quick sort or the way that Youngju told us. And then the second one is obviously the first element. Index 0 is the smallest. And the last element, index n, whatever the n is, sorry, n minus 1, is the max. That's it. So this is n log n. So we can sort this out in n log n. O n log n, right? You get it, right? Good. So if you have a strategy how you want to go about, to be honest with you, if you got, it's just practice. Just practice, and then maybe try to solve one of these questions every day that you wake up. You just set a reminder in your calendar. You just solve one of these every day. There is a website called LeetCode. It has all these algorithms. I think there is one more called Career Cup. So there are these algorithms all over there, and then these are like interview questions. So my goal is, I hope you guys are not hired. If you're hired, why are you staying in this course? If you guys are planning to apply for challenging jobs, let's say jobs, there are plenty of jobs at Google, Microsoft, Amazon, and they all look into these algorithms. So the practice, just practice every day. Just pick one of these examples. I've taken these questions from the book. You could perhaps do the same. and just go about solving it. And if you can get frequent in solving these questions, then I would say you then will hire me in the company. Once you're building your own team. Let's go to the next question. So the next question is quite simple. Construct a heap for this list. So let's, I give you, so the question is to construct a heap from this list. It's a list given to you. You have to construct a heap from it. So maybe I give you, 3 minutes. It's 8:49. We end at 8:52. I'm going to call out a name to just show me your heap tree. All right, Yal, Y-A-L. At least that's what I'm seeing from the name. Could you please explain or show us your heap tree? Yal? Is it Yal or Yal? Is that a stranger joining us? Yal? Nope. Okay, I'm gonna write the name. So this guy is not present. Right. Guang Chen Wan, would you like to show us your tree just in front of the camera? 8, what is it? 8, 6, 7. So that's 8, 6, 7. What are the leaves? Is that 6 on the left? 5, 3, 1, 4. 5, 3, 1, 4. Okay, so let's see if that's the case. Let's just fact check it. Fact check. Okay. So that's 1, 8, 6. You guys see my handwriting, right? Okay, that's good. 8, 6, and then 5, 3, 7, 4. So we always start from the rightmost, and we always from the leaves, and we always start from the rightmost leaf. Okay, that's what the plan is. 6 and 4, right? 6 and 4, they don't need to be swapped. 6 and 7, they need to be swapped, right? So we're gonna have 1, 8, 7, 6, 4, 5, 3. So far, so good. Then we come to the next leaf on the left. 3 and 8 doesn't need to swap. 5 and 8. We're all okay there. So we are done with this stage. We go back, we go up one level and do these comparisons. So between 7 and 8, which one should go to the top? The biggest one. The biggest one should go to the top. So we put 8 there. 1, 6, 5, right? Then we come back one level again to just reorder things, hippify. On the right wing, everything is good. On the left wing, things have to be reordered. Which one comes up first? Which one comes up? The biggest one, right? 5. So we're gonna end up with eight, 5, 7, 1, 3, 6. So was that 8? Yeah. So I think Guangcheng Wen was not the absolute answer. So I would say the right answer is 8, 5, 7, 1, 3, 6, 4. Did anyone get this? Just raise your hand. Half of you, maybe. Half of you. Okay. Okay. So that's the final answer here. And just make sure that we can do the same. So you start from the rightmost leaf, and you start doing the ordering, and then you go to the next leaves, and then once you're done with the leaves, you come one step up. You do that with the main root, and then you go back down to hippify again. Okay. Just make sure you can follow the steps correctly. So in the exam, I want you guys to basically draw every step for me. Okay, don't just come up with the last step and write it down. I see some of you guys have written the last step in the assignment. I don't think if that's the right way to do it. I just want to see the process that you guys are going through it, the mindsets, and just want to make sure that you guys are following the steps there. So please be elaborative on all the drawings and the steps and the sequence. All right, so let's move on to exercise 3. Outline an algorithm for checking whether an array is a heap. and determine its time efficiency. So I give you an array, and you would say if it's a heap or not. Okay, so that has to do with you know, we had some magic there for you know, to add log n over 2 for I to be 2 and for the root, this of the roots, and then we had something for left is key I 2I, and then right is I plus 1. So you guys should be able to take this, sort of reverse engineer it based on reading from every element in the main array that's given to you, and then decide if this is a heap or not. So as you're doing all these checks in here, you have to make sure that you know, first element array is biggest, right? And then you have to say also that the parent is always bigger than junior. You have to be able to confirm. So my first check would be, I look at the first element in the array. If it's smaller than the rest, or smaller than one of them, I readily say that, oh, this is not a heap, right? Because the heap will keep the max at the root, at the main parent, at the top. And if that check is violated, then you can readily discard it. You say, oh, this array is not a heap. If that check passes, then what you want to do is you want to go and find the parents based on what you're seeing at the top here, right? Based on these rules, right? And then you want to check their children. So you want to infer what the left children is, what the right children is for every parent, and you can find the index of a parent by this guy. And then based on that, you go to the left index, you go to the right index, and see if those children are smaller than the parent. This could be a midterm question. So see if you can sort this out. So I give you 5 minutes to solve this, and I call out the name again, one of you guys. So it's 9:02, we finish at 9:07. right, it's just was taking a very short break. So maybe if Jae-Young Rim can tell us how you would go for solving this.
Can you hear me?
Yep.
Sorry, I didn't really get this question. I think I need more time to solve this one.
Okay, so maybe Navneet can tell us how.
We will have two if conditions.
Just
That
just
if-
give me a high level understanding or high level way of you sort this out instead of telling if conditions. So what would be the
So-
first check?
So if the left side key, which is 2i, is less than the parent node.
Right.
You
So
do
how do you determine the parent node?
The biggest one in the array, the biggest element in the array.
Oh, that's one parent, right? And then you have to go to the next parents. How do you decide the next parents?
Next parent will be bigger than its children.
So can you show your scribbles? Can I see that? Can you come closer? Right. I cannot. So is there anyone else who can basically help Navneet in this? Ben, Red, Bob, Kathy,
I don't know.
and Adi.
I mean, I don't know if I'm any more correct, but I basically just had, I think it's O to the N, and really all I was doing is I was checking to make sure that, like, I go through every index, and then I basically just make sure, like, I check the right leaf and the left, or like the right
Yeah.
node and the left node, and make sure that it like is they're both smaller.
Yeah. So you want to write a for loop I equals 0 going to n minus 1. And you want to check for that condition. If I is bigger or equal than 2, and I is less than less or equal than n minus 1, you want to check. You want to get the floor of I divided by 2. That's going to be index of your root. Right? So that's going to be the index of your root. And then, so the rule was what? We have the parent is, log n divided by 2. So we're going to have log n divided by 2. Razor. Do that logarithmic approach. Log I base 2. That's the floor of it, right? So we have that. And then, so we have the root index. So based on the root index now, we can find the left and right. So we say 2 times root idx is the left idx, and 2 times the root idx plus 1 is the right index. Now that we have the indexes of the left and right, then we can use them to compare. Okay, so at some point after these lines, I don't have a space, but I would say the name is h. So we say h if h root idx is bigger than h left idx, and again same h root idx is bigger than h right idx. That means that you're good, right? If it is not, then we return false. You guys get the idea? And then you have to do that in this for loop. So I would urge you guys to go ahead and just take these notes and then put it in. Basically, go and implement it with your favorite language: Java, C, C++, JavaScript, Python, whatever. Python is the fastest. I would say this is like it takes 15 minutes of your time. And the way I do that, usually I go like write these as comments in my code, and I just go and implement it. This could take like 15 to half an hour. So this could be like one question out of those 5 questions of your midterm.
What does H stand for?
Well, H is the name of the array here. This question says array.
Oh,
H.
I see. Okay.
Yeah. You can name it anything. You can name it A or whatever.
Can you hear me?
I can hear you, but I cannot see you.
So okay.
The classic.
All right, sure, whatever. So can we do a little simpler? So if we started from reverse, so from the end element, and then we don't need the left and right. We could just see whatever log base 2 of the thing divided by 2, if that is the root or not. If it is, then okay, I'll continue the loop. If it's not, then like break the loop and just say false.
Sorry, can you say it again?
Yeah.
You go to the end.
So you start from the last element, and we already know what the formula is to find the parent, which is like log base to whatever index divided by 2, right?
Yeah.
And then we can floor the thing. So whatever, whether it's the left or the right child, they would have the same parent. So when we floor it, it would be the same. So we don't need to have 2 different variables saving left and right. So just see, okay,
Right.
is our n bigger?
So that's one. Okay, so that's going to be the main issue if it's not a binary tree, because heap is a binary tree, and so there is some subtlety there. What you're referring to is to even if you want to find if it's a binary tree or not, right? What the question is asking here is, we assume that it's a binary tree. We put that to represent a binary tree, but we basically want to see if it's a heap tree. So heap tree is a member of binary tree. So I think your approach is to find if it's a binary tree, because you're going to the root to see if the parent of the left and right is same, and if it is not, you say, oh, this is not.
No, that's not what I'm saying. What I'm saying is, when you're at the last element, it's basically a left or a right child, and both of them are going to have the same parents. So when you put it in the formula, which is log base 2 divided by 2 floor of that, it's going to give you the same value for left and right child. So you could just compare with that and see if the parent is bigger.
The log n2 is going to give you the index, not
yes,
the
index.
value. Yeah.
So you could use that index to find the value.
Yeah, but
then you
when
don't
you
have
find
to.
the value, you have to do a comparison because the property
Yeah.
is that the parent should be bigger than the left and right.
Yeah, then you do the comparison. So you
Yeah.
don't have to save it into this left and right variable. You just need one variable to save data. Here you need to like save it in left and right. There you could just save it in one variable
I
and then
see.
keep on
Okay.
going.
So I see what you mean. You want to just you're just reducing one extra variable.
Yeah.
Yeah, for the index.
Yeah, and you start on like the reverse. It's the same otherwise.
That could work. Yeah, that could work. Good.
Yeah.
Okay, so then the next question is, what is the time efficiency here?
I had one question though. Why do we check if I is greater than or equal to 2?
Right. So if you go back to the slide that I provided, okay, let me just go back all the way. So go back to slide number 28. You have to meet these conditions.
Okay, I see. Yeah.
Yeah. So you essentially have to meet these conditions.
Okay, that makes sense. Yeah.
So the question now is, what's the time efficiency, right? Can someone suggest the time efficiency here?
I think it's just n.
And yeah. Yeah, because you have a for loop, right? And in that for loop, you're just doing, there's a basic operation you find, and it's just one for loop that is traveling across all the elements in there. So in my algorithm, it's n. I don't know if you guys can better. I don't think if there's any better way, because if you want to do pre-sorting here, the format of the array will change, right? So the question is not to change the format or to solve something or look for something. The question is to find if the array is indeed a heap, right? So to find if an array is indeed a heap, you have to look for those properties. All right, I think this was a very good discussion. Exercise 4, anagram detection, design an efficient algorithm for finding all sets of anagrams in a large file such as a dictionary of English words. And anagrams are basically words that are having letters but in different locations. So eat is an anagram for 8, is an anagram for T. So eat, 8, T belong to one set or one class of an anagram. This is really helpful for, this could be one of your, when you're talking projects, you could perhaps look into Twitter feeds or say Facebook feeds to search for such words that are anagram of profanity or some special, like it's the election date, and people are tweeting something, so you're looking for anagrams of some special words to basically highlight. And I think that's what Twitter does. So when you have like in the news, or Google does, when there are like some trending news, it just looks for anagrams or some special words. So I think one project would be to write an algorithm that look for special words and its anagrams, perhaps, to basically highlight that news or bring to the top of the feed in your personal feed, or in the Twitter account or in the Facebook. That's one way to deal with. So if you guys can maybe spend another maybe 9 minutes. So it's 9:21. We're gonna just think about it. How you're gonna write such a such an algorithm? Just think about pre-sorting. How you would do that. I think for this question, I just want to have some high-level thoughts. I don't want you to go deep in implementation. Just give me some pseudocode. How you would do that at 40,000 feet implementation. So 9:21. We're gonna finish at 9:30. I'm gonna check attendance now. Alan Cho, just wave your hand. Jessica Chu. Yeah, we go. Ben is here. Navneet is here. Yangju Kwan. Okay, Yangju Lee. Okay, Yang Li. Okay, Yutong Li. Okay, Zichang Liu.
Here.
Okay, Nadi is here. Scott is here. Jai Young Rim.
Here.
Okay, Guang Cheng Wen. Okay, Alan Wang. Okay, Jie Zhang. Okay. Okay, so I think Yal is somebody else, or one of you guys who are having two accounts. Do you guys see the name Yal here? So I don't know who is Yal. Y-A-L. I think you're hacked. So I'm gonna put P in here, save, save. All right, so we don't have attendance check for week 7. Obviously, if you write a midterm, that's an attendance, obviously. So if you guys go back to your D2L under course tools, and if you click on attendance, you should see your attendance check marked for week 6, which is this week right now. Then week 7 is midterm. Obviously, I'm going to skip that. So we're going to have 4 more weeks before the final exam. I think the final exam is set to July 20th. And the duration of the final exam is same as midterm. Perhaps it's just 90 minutes. And the stress would be on whatever it comes after the midterm. So midterm is going to cover the first 6 chapters. And then after that, we're going to look into graph theory, some dynamic programming perhaps, and that should conclude our course for this term. All right, you guys have 5 more minutes. Just take your time to answer this question. I think this is the last question I have. Yeah, this is the last question that we're gonna solve in class today.
Are we given the word which we have to find the anagram of?
Right. So we assume that we basically we tokenize the sentence. So let's say you're given an what's the max on Twitter account? 250 words.
something like that.
I think in Twitter you cannot go beyond 250. So you're given the feeds and then you tokenize it. So you tokenize based on the space. So every word is an element of an array. Then you have to do something with it.
But do you know what word is the basis for your anagram finding, or is every word considered an anagram and then you find the anagram of that thing? So, for example, if a sentence starts with the whatever, so okay, we take that's one of the anagrams we need to find. Whatever is the next word. So now that's also something we need to find. So
this is a sentence.
that,
Hello. I ate tea yesterday. Something like that. So you have to tokenize it. 1, 2, 3, 4, 5, right? And then you have to see which one of these words are anagram to each other. So if I look at, but just visually looking at it, because I'm human, I can just readily say that these two are anagrams.
yeah. So what you mean is like every word, after tokenizing, every word is considered a separate entity, and we have to take one by one and check.
Exactly.
Okay.
Now the question is how you can improve it, because what you explained to me is a brute force approach, right?
That's the easiest way, yeah.
Yeah. So give it a thought. Maybe I extend it to 5 more minutes. At 9:28, we finish at 9:33. I'm gonna call out a name. Could be Erica or Navneet or Alan, or don't improvise a name. Right, guys. So this is the last segment we have today. Ben, do you want to explain?
Yeah, I kind of have a rough idea here.
Okay,
So,
go ahead.
all right, so there's going to be 2 for loops, and I'm treating this as you have like I'm treating this like a 2D array.
Mhm.
So you iterate through the sentence, and you stop at each word, and you store and you create a dictionary, which basically stores that word's position in the array, its length, and its frequency. And you do this for all the words, but there you have an initial check, which checks if a second word has the same length and frequency as another word. You add this to a second dictionary for anagrams, which stores those 2 words' position.
Yeah.
And then after iterating through the entire sentence, you then return, since you have those 2 words positions in the array, you can just return that to the user.
Right. Good. So anyone wants to add? So I think the first catch is to look for categorizing the words that are of the same length, same number of letters. So so when it comes to anagrams, obviously, we wanna. So for this example, eat, ate, and tea are all of same length. They have 3 letters, right? So we basically have, the first thing we can do, this is just one solution, one rough idea. I think Ben is correct. So what we have to do is we have to basically look for, in this case, 3-letter words. So that's one category. Then we have like 4-letter words, So we basically tokenize the words and then see what's the biggest length word that I have in terms of letters, and what's the smallest. Obviously I, so I is of length 1, and the biggest is 1, 2, 3, 4, 5, 6, 7, 8, 9 is yesterday with 9. So I'm basically having a dictionary that is categorized based on the number of letters for words. So once I have that category, I go to each category, and and so I basically have something like I have, it's just a rough idea. This is one solution. I can show you I will show you the book solutions later. So so basically I have so this has to deal with the system design. I don't think if you guys are expected to come up with actual implementation, so I come with a dictionary, right? And that's a key value. So the key is the number of words. So 1 word, 2 word, 3 word, 4 word, all the way. In my case, the biggest I have is 9 word. And for every category, I have a linked list. So for 1 word, there's just I, letter I. 2 word, I don't have a 2 word here, so there's nothing here. For 3 word, I have eat, 8. It's just a linked list there. I just add it to the linked list, right? 8, and yeah, that's it. That's all I have. 4 word, 1, 2, 3, 4. I don't have anything here. I'm just hello, I ate tea yesterday. I am solving for that. There's a 5 word, and that is hello, right? And then there is a 9 word, that is yesterday. So once I construct this type of a data structure, a dictionary, which each element is having a linked list, I go to the set that is more than one element in it. So in this example, I have this set. And now what? What can I do now? Any thoughts?
Return those to the user.
Not exactly. I mean, we just picked the words that are of same length, but we don't know if the letters, if they contain the same letters, right? So for doing that, we can do some pre-sorting, and perhaps we can do a quick sorting here to sort this guy and sort this guy based on alphabetical order, right? So if you sort this guy, it's going to be A, E, T. If you sort this guy, it's going to be, you apply a quick sort again, A, E, T, that's N log N, right? And then once you sort it, then you can see if they are equal or not. So if they are equal, you have anagram. They are anagram of each other. If they're not equal, then they're not. Okay? So this is one example, one solution. Is there anyone who has come up with a, clever or more efficient way?
I guess it's not really more efficient, but I thought about using the ASCII value and then changing it, making it into like an array, and then use the heaped version after the heap sorted it, and then compare if they're identical.
Yeah.
But it's kind of like, I guess it's kind of taking a long way, because you can just simply, as you said, like do a quick sort and then just compare the two words if they're identical to each other.
Right. But you still have to do categorization based on the number of letters for every word, right? So you have to group the words based on their letter length. And once you group them, then you go to that particular group and then check for the anagram. So I can tell you that, for example, for the first group where there is one letter words, you can readily discard it. I mean, unless there are two eyes, obviously, but this is kind of redundant. So I readily discard it, right? And then you start from 2-letter words, and 3-letter words, and so on.
What is the time complexity of your algorithm? Is it n square log n?
If you are, no, I think it's n log n, right? No. N is squared log n, because, so you have n log n here. And then for constructing this, it takes n. So I think you're correct, n squared log n.
Okay, so what if instead you do, because if it's is n squared better than square log n?
Is n squared, n squared is faster than n squared log n, because log n is an additional component, right?
Yeah, so what if you do something like, you basically create a function with regex. So you're like, okay, you take whatever this word is, you send that into the function, and then it's like, okay, H, E, L, those are the 3 words in that. And so it basically checks if initially there's a space and at the end there's a space, and if there's any iteration of H, E, L, and if they have the same length. So you keep on checking that for every word. So that's loop. So it's basically a n squared thing. So because initially you start from the first element, go to the last element, then you do the second element, you go to the last element, and go on, so on and so forth.
Right. So what you're trying to do is before you find a space, you want to do key matching so you do a substring match in a string. I think we solved one of these problems in I think it was second class. So what you're trying to find is find substring in a sentence. That's what you're trying to do. That's totally fine. You could be doing that until you find a space, right?
So okay. So for example, we have hello, right? So we would a regex which would check is there H, E, L, or O in the first element. That's
Yeah,
one
yeah.
rectangular box. Then in the second, it would check
Yeah,
the same thing,
Yeah,
whatever the length is. So
Yeah.
if it's hello is 5 lengths, so it's like 5 lengths of H, E, L, O.
Yeah.
Is there that matching? And then if it matches, okay,
yeah.
go to the
yeah.
next element.
Yeah, good. Excellent, yeah.
Yeah, that should be
that
n
works.
square, I think.
That works. Yeah, that works. That works. Okay, I think we had a sufficient discussion here. So you guys, I hope you guys have written some notes so that if I give you a similar example in the midterm or final exam, you guys should have a strategy to solve it. I think we had enough discussion. We basically contemplated 2 different methods. The last question is about efficiency. So I think you guys have to really go and implement merge sort, quick sort, and heap sort to be able to answer this question. I'm not gonna, this is like a take home. It's not gonna be in the exam, but if you guys are interested, you can take different sizes and then you can draw it. MATLAB would be the best. So what you can do is you could have something like, let me just write something. So you could have a graph that in this graph, the x-axis is n. So this guy is n. So this is 10 to the 2. The number of inputs is 100 or 10 to the 3. 4, 10 to the 5, you know. So this x-axis is shown. I'm just, it's logarithmic scale, right? Scale. And then the y-axis would be the time, like in microseconds. And then you show a trend for every one of these, you know, like which one is the fastest. So let's say the quick sort is going to show something like this. If it's logarithmic, it's going to be linear. So you're going to have like this, quick sort. And then you're going to have something for you know, like a merge sort. And you're going to have a similar trends because they're all n log n. And if your x-axis is in logarithmic scale, then it's going to show things in linear trend. So you're going to have something in maybe. And that's for heap sort. This is heap sort. Yeah, just to get an idea which one is the fastest. You know, you can randomly create some inputs up to that scale, and then do some metric analysis for understanding how the order of growth is for different inputs. So this is just out of your interest. Obviously, we cannot have such a question in the midterm or final exam, but this could be something interesting that you guys could be implementing to just see how n log n in different algorithms would look like. Okay, and then the question is, you do that randomly one time, so you randomly generate you know, this much of data sets. And then the second time, you do in an increasing order, And the third time you do in decreasing order and you apply different sorting algorithms. So you're gonna end up one graph for this, one graph for this, one graph for this. That's the basic ideas. Okay, so see if you can do that at home. And yeah, are there any questions here? You all good? Yes. All right. Oh, there we go. Okay, so that should conclude our session today. Thanks a lot for your attention, and I will put the midterm next week at 6 o'clock. Next Tuesday, 6 o'clock in the evening. You guys should have 90 minutes, depending on, I think 90 minutes to answer the questions. There are going to be 4 or 5 questions, and it's going to cover the first 6 chapters. If you have any special questions, just get in touch with me in a Slack, and I will be able to answer you back within 24 hours. I know that some of you have asked me to remark your assignments. So if you guys want me to remark anything for you, you first have to go through the solutions I provided and tell me that the solutions are matching with your answers. And if that's the case, then you have to articulate what questions you want me to remark. I wouldn't be able to remark everything, but let's say you say, okay, assignment 2, question 3, I'm going to remark it for you based on the answer that I have from my records. So if you guys do that, then I would be able to go and remark it for you. Okay, so other than that, you're out of time. It's already 9:50. So I see you. I try to be online next week, but I don't think if you would see my face. I would be online during the midterm, and then you would be able to write the midterm. You pick it up from D2L and submit to the right Dropbox, and that should be it. Then I see you after. All right. Thank you very much, and have a good evening.
Thank you.
Thank you.
Thank you.